Good evening, one and all. A warm welcome to the fifth session of International Webinar Series, jointly organized by Department of Chemistry and Center for Research and IQAC Beselis College, Kottayam. We started our series on 13 November and have completed 4 sessions on current and emerging areas of chemistry, which were handled by academicians and scientists from reputed institutions across the globe. Today, we move on to the fifth session of our international webinar series, which will be handled by Dr. Prasanth Menezes, Material Group Leader, Division of Inorganic and Analytical Chemistry, Technical University, Berlin. So with immense pride and pleasure, we, the Department of Chemistry, wholeheartedly welcome you, sir.
Thank you.
May I now invite Dr. Miki Thambi to introduce our speaker.
It's my special privilege to introduce today's speaker, Dr. Prasanth Menezes, the Group Leader of Inorganic Materials in the Chemistry Department of Technical University of Berlin, Germany. His research focuses on the design, development, and structural understanding of novel, unconventional catalysts. In the heterogeneous catalysis, especially in the area of redox oxygen catalysis, electrocatalytic water splitting, as well as electrochemical redox reaction. He has published around 100 high-impact original research articles, over 3,300 citations and book chapters, and even has 3 patents to his credit. He has delivered talks in the numerous conferences around the world and has received several awards throughout his research career. He was a distinguished speaker at the United Nations Initiatives for the Sustainable Chemistry. Further, his innovation based on the non-noble concept for the wastewater treatment was also highlighted at the German Research and Innovation Forum, which is under development towards the founding startup. Recently, he has figured among the top 2% scientists in a global list compiled by the prestigious Stanford University. Dr. Prasanth obtained his PhD from the renowned Max Planck Institute, Germany, in solid state and structural chemistry, and then moved to the prestigious Technical University of Munich to conduct his postdoctoral research in the direction of the inorganic chemistry with a focus on novel materials. He conducted research on Lewis acid doped polyaniline at the reputed Indian Institute of Science, Bangalore, before moving to Germany to pursue his doctoral studies. He is also an alumnus of Mangalore University and also Indian Institute of Science, Bangalore. On behalf of Department of Chemistry, Beselis College, let me welcome Dr. Prasanth Menezes for our today's webinar for handling the topic Emerging Materials for Energy-Driven Water Splitting. Once again, I welcome you, sir.
Thank you. Thank you so much.
Thank you, sir.
We are moving on to the technical session. Participants, please mute your microphone. And if you have any queries, you can ask the questions in chat box. Thank you.
So may I start now?
Yes, sir.
All right. Can you see my screen?
It's coming. Yes, sir. Yes, sir.
Okay, and you can hear me properly and you can see my screen, yeah?
Yes.
All right, so let me start my talk. First of all, I thank you guys for inviting me to deliver this talk. And today, the topic of my talk would be emerging materials for energy-driven water splitting. Before going to the talk, I would like to show you some glimpse of Berlin. So this is okay. So this is the map of Europe, and you could see that Berlin is in somewhere center of Europe, and it's also the capital of Germany. So these are some of the very important places in Berlin. So this is the top view of Berlin, how it looks like from the top. And this is very famous, historically very famous Berlin Wall, which separates East Germany from West Germany, or let's say East Berlin to West Berlin. This is one of the very famous monument, which is called Brandenburger Gate. Berlin is also very well known for shopping. So this is one of the shopping streets in Berlin, which is called Friedrichstraße. That means Frederick Street. Not only for history and shopping, Berlin is also well known for its parties. A lot of young people around the globe, they come to Berlin for partying. Um, However, at this point of time, we are under lockdown, so there is nothing going on in Berlin. All right. Let's say in Berlin, we have 4 different universities. As you could see, this is the Technical University of Berlin, where I work. And then we have Freie University, Humboldt University, and Potsdam University. So from the number of students, you could already imagine that these universities are quite large. And this is the campus map of Berlin. So the TU Berlin is in the heart of the city. So this is where the chemistry building is situated. As you could see, this is a very old building, but somehow it's very, very spacious. Okay, let's go to the topic. So today, I would like to introduce some about one of the hot topic which is going on presently. It's called water splitting. Then I would come to photocatalytic water splitting in a very, let's say, brief way. And then I will go into electrocatalytic water splitting. There I will show you a couple of examples, which are the emerging materials and why we are interested in this topic. And finally, I would like to show you a small summary and outlook. Okay, so to do that, first we should know what is our primary energy source. So if you look at this figure, you would see that in early 18th century, we had wood as our primary energy source, and then came coal. And between 1950 and 2000, we had given immense importance to oil, nuclear, and natural gas. Where do we stand presently? So if you look at here, somewhere here, we see that we have taken over by natural gas, nuclear, and even oil. However, if you look at this curve, you see that the world is pushing towards renewable energy technology. Why? This is the question to be answered. The main and the important reason is the environmental benefits and economic benefits of renewable energy technology, which includes you can generate energy that produce no greenhouse gas emissions, such as carbon dioxide, from which you normally get if you burn fossil fuels. And this makes reduction in pollution, air pollution. Another impact factor is you can really diversify the energy supply and reduce the dependence on the imported oils which you use on our daily basis. So this is what you can see what happens in Germany. How is the energy production? What you see here is the percentage of energy consumption and the production. So if you look at it, Germany is producing 37.6% of renewable energy. And the rest of the energy comes from lignite, hard coal, natural gas, and nuclear. Within this 37.6%, what you could see is that the major amount of energy is produced by wind power, and almost similar amount of energy is produced from solar power and biomass, and a tiny amount is produced by hydropower. So there is a huge demand for an alternative, or let's say renewable energy technologies. I will show you 2 figures. What is the situation or scenario in Germany? So if you look at these 2 figures, you will understand. This is the scenario was taken for Germany in summer 2017, and this was for winter at the same time. And the difference is that in winter we have no sun in Germany, so that's a limited amount of sun. So what you could see, this is the amount of energy required in Germany. However, how much we are producing, which is through renewable energy, is shown here. This is the solar energy, which is shown in yellow, and blue is wind energy. And we see there is a huge gap. But if you see, or if you look at this figure, in winter we have no sun, as I said already, and there is the demand remains the same, the production remains very low. Therefore, it's very important to have an alternative energy source. Now, hydrogen could be an alternative energy source in with respect to fossil fuels, because if you burn fossil fuels, what you are getting is energy, of course, but a lot of carbon dioxide, which we don't want to have. On the other hand, if you take hydrogen, or if you burn hydrogen, what you get is energy, but the byproduct what you get is also water, so which is very safe. And hydrogen is not only important for let's say energy, but it's also important for many chemical reaction, and also it is constantly used in chemical industries to produce fertilizers. Okay, one of the interesting fact, almost 3 to 4 months ago, Germany had decided to invest almost 9 billion euros for hydrogen economy, and they cite that most hydrogen used today is produced by reforming natural gas, which releases a lot of carbon dioxide, which is harmful for us. On the other hand, green hydrogen is extracted from water electrolysis, that means water splitting, which is still a very energy intensive process. That means it is not so easy, because you need a lot of energy to produce hydrogen from water as well. So now let's say we want to split water. So what are to make hydrogen? So what are the routes we have to do this? So as you can see from this picture, there are a number of ways how we can produce hydrogen for water. For example, you could see a biochemical energy way and the thermal energy, and you can couple thermal with biochemical and come out with thermal biochemical way. Similarly, you can use thermal and electrical, and you can couple them together, thermoelectrical. However, presently the research has more focused on electrical energy, photochemical energy, and also coupling of electrical and photochemical. So this is the most emerging areas at presently. A lot of people are really concentrated on photocatalysis, electrocatalysis, and photoelectrocatalysis. So as I said in the beginning of my talk, I would speak a little bit on the materials. When I talk about materials, the materials is what we call catalyst. So from your basic chemistry classes, you would be knowing that a catalyst is a substance which increases the rate of the chemical reaction, but doesn't go under permanent change. So this is the energy diagram, which you could have seen in many textbooks. So you have reactants and you have products. What happens if you have a catalyst? What happens if you don't have a catalyst? So if you have a catalyst, then you are minimizing the energy barrier and minimizing the activation energy, and then you are forming product very selectively. If you don't have a catalyst, of course, the energy barrier would be much higher. So to cut the story short, if you have lower activation energy, your reaction is very faster to form products. That means a catalyst lowers the activation energy, reduces the energy cost, and accelerate the whole reaction. Now, I would be showing you something about photocatalyst and electrocatalysis. So I would just want to introduce you the terms photocatalyst and electrocatalyst here. A photocatalyst is a material that absorbs light and bring it to higher energy level and provides those energy to make a chemical reaction. Similarly, electrocatalyst is simply a catalyst that participate in the electrochemical reaction. I'll explain you these factors in the coming slides. But at this point of time, one should understand that the textbook definition doesn't hold good for in heterogeneous catalysis. So unfortunately, most of the heterogeneous catalysts which are used for chemical reactions or catalytic reactions change during catalysis, at least on the surface. So in general, they are called pre-catalyst. Okay, so now I would talk about photocatalytic. I will not go into the details, but I will just want to show you how this photocatalysis works. Okay, now let's imagine we want to split water. So what do we need? I mean, if you look at the reaction here, it's very, very simple. What you need is water, and then we can produce hydrogen and oxygen. This means what you need for a photocatalyst, you need a photocatalyst and abundant sunlight. That's enough in principle. Now the question comes, is that easy? So think about a situation. This is the a semiconductor, and you know from the semiconductor chemistry that you have valence and conduction band in a semiconductor with a band gap. So the main point is when you shine light on semiconductor, you are creating electron hole pairs. That means your electron from your valence band jumps to the conduction band, and the hole comes to the surface of the catalyst or the semiconductor to oxidize water to form oxygen. Please remember that oxygen means oxygen is produced through oxygen evolution reaction. And similarly, the electron moves towards the surface to reduce water to form hydrogen. Is this so simple? No. Again, it's a bit complicated because when the electron hole pair are separated, they always want to come back immediately to their resting position. That means when the electron goes to the conduction band, it doesn't want to stay there, that it wants to come back immediately to fill up this hole. So how we can avoid the situation? We can use something called co-catalyst, which is a nano catalyst. We can put it on the semiconductor. What it does, the moment the electron goes to the conduction band, it traps the electron. The moment the hole is created, it traps the hole and oxidizes and reduces water respectively. Okay, of course, this looks very simple, but in general, such semiconductor do not exist. So this is some of the bands, some of the materials and the band structure of the semiconductor, as well as the redox potential of these semiconductors. What you could see here is that this is the redox potential of to form hydrogen, and this is the redox potential oxidation of water to form oxygen. And there is no semiconductor which exactly fits these two, the gap of these two potentials. Yeah. So in general, you cannot make overall water splitting. That means you cannot produce hydrogen and oxygen at the same time. What we can do, we can split it. That means we can make a half reaction that is only for hydrogen evolution reaction, and we can make a half reaction for oxygen evolution reaction. Now, how does it work? So this is the same semiconductor what I showed you in the previous slide. So you inject, or let's say you have an incident ray from your light, and then you hop your electron from your valence band to the conduction band. What you immediately do, you quench the hole. So you give a, let's say you introduce a donor molecule which donate the electrons to the holes. So the holes are filled now here, or let's say quenched. And the electrons are available here, and you use those electrons to produce hydrogen. Of course, in the other situation, what you can do is you can use the acceptor molecule. The moment the electron is excited, you take the electron out of the system, and then you use those holes to oxidize water. So this research is very popular now because we cannot deal with such a situation where we can produce hydrogen and oxygen at the same time, but we are convinced that we can do this half reaction very efficiently. Just to show you some of the photocatalyst what we have worked in the last few years, this is something called cadmium selenide, which has a band gap of 1.7 electron volt. And then we have cadmium sulfide with the 2.4 band gap. And recently we were working on carbon nitride, which is the organic semiconductor and has a band gap of 2.7 electron volt. This is the structure of this carbon nitride. This is very promising. These are the very promising catalysts for hydrogen evolution reaction. So as I showed you this again, the same from the previous slide, this is what we want to do. We introduce a donor molecule and quench the hole, and we want to produce only hydrogen. So that can be done using triethylenamine as an electron donor, which donates electron to quench holes and gives only let's say electrons to reduce water to produce hydrogen. So we have done some of this work using carbon nitride as the photocatalyst, let's say this semiconductor. And what we did was we introduced some kind of nickel phosphide nanoparticle on the surface of carbon nitride over here. Yeah, it is shown here with the black dots. And what we can do, we can quench the holes, but we can take the electron to this particular material, which is nickel phosphide, and we can use those electron from nickel phosphide to generate hydrogen. Well, we also did some more experiments with the nickel salts, and they're very efficient. I mean, this is a very good strategy to produce hydrogen. However, as I said, we cannot produce oxygen from the system as we are quenching those holes. Okay, how we can produce hydrogen in a lab scale? I want to show you a video if it works. Most of the time it works, but I'm not sure whether, I don't know. Okay, it doesn't work. But what I wanted to show you here is that how we can produce hydrogen in a lab scale. So this is very easy. You take your carbon nitride in your vessel, and then you shine your light, and finally you can generate hydrogen, which goes to the top, and it remains on the top of the cylinder. Okay, I couldn't show you the video, I'm sorry, but what I can show you is that the large scale setup, what we have done in TU Berlin. So this is a very large, this is a large scale setup. This is with the area of 1 meter square. We kept this area because we wanted to produce a lot of hydrogen. This instrument has put on the top of the roof of TU Berlin. And this is a test reactor. We wanted to show to the public that we can really produce hydrogen just using sunlight. So as you see that we took the same carbon nitride on some plates, and we shine light, that is in our case sunlight, and what you can see, the bubbles here are the hydrogen evolution. Yeah, and we could produce 40 to 80 milliliters of hydrogen per day, per hour, depending on how much sun we have in Germany. So this was done in summer. So you could see that in the case of during the day it goes up, and in the night it is stable, because we do not have any sun in the night. So it doesn't work without sun. All right, so this is just to show you briefly that this system can work, and this is a very challenging situation because photocatalytic water splitting is very, very difficult, because although we have a lot of sun, it doesn't work because we need a very good semiconductor and a lot of different aspects to consider. So in this regard, a lot of people are also working in the alternative pathway, which is electrocatalytic water splitting. So I will show you in a bit detail how electrocatalytic water splitting works, and how we can do electrocatalytic water splitting using different materials. I would probably introduce you, if I, depending on the time, two different novel functional materials which we could use further for water splitting devices. So this is a typical electrolytic cell for electrocatalytic water splitting. Okay, and what you can see here is anode and a cathode. Very simple. We need two compartments. One is anode and a cathode. What happens in anode? Oxygen evolution reaction. The material is oxidized to produce oxygen evolution reaction from water. Here, this is a cathode. It is a reduction compartment where the water is reduced to form hydrogen evolution. So this is very clear. So reduction means hydrogen evolution. Water oxidation means oxygen evolution reaction. Okay. Now, so what are the important materials which could do that? The problem here, what you see, this is the volcano plot, how we call it. And you see top of the volcano plot are all noble metals, which are very, very expensive and very rare. And don't care about these factors. This is something to do with the O potential and the surface oxygen binding strength. I would not go into details, but what I want to show you is that the only noble metals are active in a high efficient way. Why? The question is why arises because you have this water oxidation reaction here. This is the equation. So water oxidation is a four-step process. Like four electron transfers are involved to liberate one molecule of oxygen. So this goes through four steps. So each electron transfer is very, very important. You take water, you're forming hydroxyl species, then you have second electron transfer, then you have adsorbed species, then you have third electron transfer, you have OOH, oxyhydroxide species, and at the end you produce in the fourth electron transfer a molecule of oxygen. Okay, but the first three, or let's say first two steps are quite easy, not so energy demanding. However, the third step or this step is very, very energy demanding, and to produce a molecule of water, one has to satisfy this step. So this step is very difficult. That's why it is called rate determining step. So if this step is compensated, you could probably have faster kinetics of the whole reaction. Okay, now if you go to the other side of the reaction, which is hydrogen evolution reaction, again what you see here is all the rare materials are on the top of the list. So our aim is to construct a cheaper system, right? So these are very rare materials, and then we do not want to use such materials. If you look at the equation, this is only two electron transfer process. So you need two electrons to make one molecular hydrogen. So this is the equation, but it's easy. You just need two adsorbed species to produce hydrogen. This step is relatively easy, but this step is very, very complicated. So a lot of research is going on to satisfy or to make it easier the process of oxygen evolution reaction. As I said, at the end of the day, what we want to construct is a cheaper system. You have a system with producing oxygen evolution reaction and hydrogen evolution reaction with cheaper metals, not using all these rare earth metals or rare metals or noble metals on whatsoever. Very cheap metals we want to use. However, we have to also think that these technologies already exist. So this is a proton exchange membrane electrolyzer which produces hydrogen, and this is the alkaline electrolysis which also produces hydrogen and oxygen. But one thing we should remember, that in proton exchange membrane cells, the cathode is platinum, again very expensive. The anode is iridium, again it's an expensive process to produce or split water. On the other hand, you have alkaline electrolysis. You have cheaper materials, which is nickel, and also cheaper materials for anode and cathode. For anode we have nickel cobalt iron, for cathode we have nickel carbides. In principle, we have a cheaper system here. So a lot of research has now focused on alkaline water electrolysis, because you could immediately start with cheaper materials, but the problem is the efficiency is not so high. So there are some requirement how the whole system should look like. For example, in order to run this kind of electrolysis, we need to have very high current density, which I will show you in a while. And also we have very low cell voltage. So the energy what you give should be very, very little. Yeah, and the current what you generate should be very high. Here the current means the amount of hydrogen production. Not only this, the most important factor is that if you use a system, the stack lifetime should be very high. At least the system should run for 20 to 30 years for alkaline, or at most 20 to 30 years for acidic, or let's say proton exchange membrane electrolysis. Okay, as I said, these conditions are very difficult to meet. Presently, people are, or most of the research groups are working on alkaline electrolysis, which is somehow very important because of the less noble materials. So this is our strategy for water splitting. So as I said, this is the if you have a two-compartment cell, this is the anode and this is the cathode. So usually nickel iron based catalysts have been used for alkaline electrolysis. So this is the O potential, which I'll show you now in a while. So this is the O potential for hydrogen evolution reaction, and this is the cell potential for overall. That means we are producing hydrogen evolution and oxygen evolution at the same time. Okay, this is the O potential. That is, lower the O potential, better the efficiency. I mean, we are giving less energy to the system. Yeah. Okay. The group, my group, works on let's say uncovering novel class of functional materials for water splitting with high energetic efficiencies. So what we do is we produce materials with different synthetic approaches, such as molecular or solid state or solvothermal or many other solution based approaches. Then we characterize them thoroughly with powder XRD, scanning electron microscopy, transmission electron microscopy, X-ray photoelectron spectroscopy, and so on. And then we use those materials for catalysis. We use them as catalyst for our catalytic purpose. We use for chemical, photochemical, electrochemical, and photoelectrochemical uh, reactions. And then at the end, we want to understand the system, why they are better, why they are not good. So therefore, we do some mechanistic insight. We try to find some mechanistic insight based on some of the operando technology. Operando means the technology where we can see what's happening on the surface of the catalyst in real time. So exactly at the particular time when the reaction occurs. Okay, now let's imagine that we have synthesized some powder. Let's say you did an experiment and then you got some powder. Now we need to deposit those powder on some electrodes to use it as an anode or cathode. The great choice for such electrode substrates are ITO or FTO or nickel foam. Why? Because if you use ITO, which is called indium tin oxide, they are very traditional. They have been used for many, many electrochemical purposes as substrates. And they are very traditional, transparent, conductive. They can easily, any powder, you can deposit very easily on them. And they're also very stable in varying potential range. You can apply any potential within this water splitting system, they're stable. But very recently, a new electrode substrate such as nickel foam has come into play because they are also very good with very good conductivity. They have a very porous surface and they have improved mass transport. That means when you produce your hydrogen and oxygen, you don't want to have your hydrogen and oxygen at the same place. So you want to move them to out of the system. So since they have three-dimensional pores, they just transport the oxygen and hydrogen from the system. They're relatively very cheap. And also, as I said, like FTO, they're also inert in operating conditions of our reaction. Okay, now imagine that you had powder, you have substrate. Now, how we can deposit powder on the substrate? So there is a simple method which we are using since many years. So this is called electrophoretic deposition. What you do, you use your FTO or nickel foam here as cathode, and then you take your powder in acetone solution and you add a little bit of iodine. In this reaction, a keto-enol tautomerism occurs, and then what you form is protons at the end. These protons are adsorbed on the particles, and when you apply the potential, they migrate towards the electrodes and nicely deposit on the electrodes. So you had powder, you know what is your substrate, and now you know how to deposit them on your electrodes. So at the end, how do they look like? So do look like this. So this is a powder, oxide powder deposited on FTO film, and this is the oxide powder deposited on nickel foam. So we can now use them directly as anode and cathode for our electrochemical reaction. Okay, now we should know how to measure them. So we could measure, I already told you and already showed you in the electrolytic cell that we could use such an overall system. You can use an anode and a cathode, or we can use a 3-electrode system where we can use a working electrode, a reference electrode, and a counter electrode. However, the problem is that every country or every research group is producing a lot of powders or a lot of investigation on water splitting. Now the problem what we have is which catalyst is better. That's the question now. How do we determine which catalyst is better? So for that, the field has come out with some norms. So everybody should look at certain points, and they should tell us or publish that whether these factors are important. For example, one of the important factor for such electrochemical reactions is overpotential. Now look at this picture. So this is the potential what you need to oxidize water. This is 1.23 volt. So whatever energy what you put beyond this, or whatever potential which you put beyond this, is our O potential. So that is the difference in thermodynamic potential and the potential at the reaction occurs. So this is the thermodynamic potential. Similarly, this is for hydrogen evolution reaction. What you could see is that this is the thermodynamic potential for hydrogen evolution reaction, and then whatever potential we put extra is our O potential. As I said, no catalyst can show this potential because this is the very ideal condition and this is not possible. However, you always can judge whether your activity is good or not by this O potentials. In addition to O potential, there are some other factors. As I already told you, stability is very, very important. How long the system can be stable. And then we have something like Tufel slope, which determines the efficiency of the reaction, how fast is the kinetics. Then we have electrochemical surface area, how much active surface is on the film. And then we have something called turnover frequency, how much we can produce in which reaction time. Then we have mass and specific activities, how much amount of sample if we take, and how much how much current we can produce. And then we have impedance spectroscopy, which gives us the charge transfer resistance between the electrolyte and electrode interfaces. And finally, the Faraday efficiency, which means how much charge you put and how much output you get. So how much charge you are putting in and how much hydrogen you are getting out. I will not go to any details because this is very complicated, but what I would show you in probably in the coming slides is only O potential and stability of the system. This is the most important factors to run the electrochemical system. Okay, so now I would like to introduce you a couple of examples. First, I would like to show you that we have discovered a new class of materials for water splitting, which is called metal borophosphate. Why we started to work on this topic? Because a study from Harvard and Stanford, they showed that cobalt phosphates can be very good catalyst for oxygen evolution reaction here. And also they came up with another report that nickel borate could be better catalyst for oxygen evolution reaction. Similarly, a group from Korea, they also showed that crystalline cobalt phosphates are very good catalyst for oxygen evolution reaction. And in the meantime, a group of France also came out with a report that they could be used for hydrogen and also oxygen evolution reaction. So from this slide, what we can show that phosphates or borates could be an important class of materials, because most of the catalysts which are used in the literature are oxide materials. So, and we wanted to go away from oxide materials because there's a well studied and there is no improvement in the activity what we could see now. So we want to go away from it and want to find out what happens if you use some structures with anionic parts, anions, or some doping, or and so on. So this is one of the important aspect we should look at it, not the presently and even for the future. Okay, so the question we had to ask ourselves, can we use the combination of borates and phosphate, that means borophosphates, for water splitting? So what is the borophosphate? So borophosphate is a system which consists of a metal octahedra, boron oxide, and phosphorus oxide. That means you have a tetrahedral phosphate, tetrahedral borate, and you have an octahedral, let's say, metal, and you have it in water, and you make a system out of it. That's called borophosphate. Borophosphate is an anionic partial structure. So it has to connect to the metal to form a complete structure, but I will show you in the next slide. So they are divided into several categories. This is not important. This is just to show that this is a large class of materials what we have now. So tetrahedral means you have tetrahedral borate and tetrahedral phosphate. Mixed coordinated means you have trigonal planar borate and tetrahedral or phosphate or borate. Anion means you substitute an anion. Borate phosphate means they are separated from each other. This is not important. What I want to show you is that the largest class of materials in borophosphates are tetrahedral. That means you have only this and this part. Okay, so this is some chart about dimensionalities and boron phosphorus ratio. What you could see is that if you increase the phosphorus ratios, you are forming framework, layers, chains. And if you use the boron ratio higher, you are forming mostly mixed coordinated with chains. So how do they look like? You see, this is the schematic diagram of oligomer, ring, chain, layers, and framework, and they are connected with metal octahedra to form the complete structure. In borophosphate, the most, or let's say the biggest family of materials are helical borophosphate. What are helical borophosphate? They are wound round 6-1 right or left-handed helices of borophosphate. As you could see here, they could be either left or right. And there is a nice water channel inside this structure. Structurally, they are very, very interesting, and they have a specific morphology which is called hexagonal bipyramid. And they somehow resemble to the structure of DNA, which is this is the double helices of DNA. If you look at this, they are also left and right-handed. And now how this structure is connected. So as I already told you, these chains, or let's say these helices, are connected to metal octahedra to form the complete structure. So if you look at the formula, we have lithium, and then we have metal, and then we have borophosphate anions. So these are the borophosphate anions. This is the metal octahedra, and the one which is in the yellow color is the alkali metals. Very nice structure. You have a dense close packing of rods. You could see nice helices and going down the structure. And interestingly, this is one of the most interesting aspect that you could see the structural similarity of helices with the alpha quartz. This is the most common compound which you see in sand, and it's also very close to the chiral zinc frameworks. These materials are very well known for adsorption, gas adsorption. This is somehow zeolite modified frameworks. And okay, so now we know that we could produce such cobalt borophosphate. How we can produce them? We can produce them from hydrothermal synthesis. That means we can make them under high pressure. You take water, you use all the precursor in an autoclave, and you heat the system. Under pressure and elevated temperature, your precursors dissolve and form nucleated borophosphate, and then slowly they grow, and then they form a nice single crystals. The picture of single crystals are shown here. As you see, they are nicely shown on from the scanning electron microscopy picture. This is the optical microscopy picture. They are pink in color. Here, this is the XRD pattern. Don't be afraid of this pattern, but this is just the XRD pattern. This is refined through Ritfield measurement. This reflexes indicates the Miller indices of the particular system. Okay, so this hexagonal bipyramid is have also holes. They are almost 1400 nanometer large. And as I already told you, we took this material and electrodeposited on FTO or nickel foam substrate, and we then did electrochemistry with it. We did all the reaction in potassium hydroxide electrolyte. As I told you, why alkaline electrolysis is very, very important. And what we see here is the cyclic voltammetry curve. So this is our thermodynamic potential to produce oxygen, but we are far off from the thermodynamic potential, and we are having almost 290 millivolt of potential, or let's say O potential. We need to reach 10 milliamp of current. That means this 10 milliamp is the 10% of solar to fuel energy converter. So if we want to benchmark the system, we always show the O potential at 10 milliamp per centimeter square. Okay, this is our O potential. We also show you on FTO glass and also from nickel foam. You see that on nickel foam, the O potential is rather decreased. That means we have a better activity on nickel foam. This is because of the electronic conductivity of the substrate. Nickel foam is electrically very, very conducting. So therefore, we have better activities. And this O potential, what we show, is much better than the ones which we tested for noble metals, which I already showed you in the volcano plat, that all the non-noble metals are very good for oxygen evolution reaction. But we show that a cheap metal also can be used and could be implemented in electrolyzers. And as the stability is one of the important factor, we also test the stability exactly at this 10 milliamp current, and we show that they are very stable at least for 40 hours. Now, once we know that this system works for oxygen evolution reaction, we try to check it for hydrogen evolution reaction as well. This is the curve, linear sweep voltammetry curve for hydrogen evolution reaction. Zero is the thermodynamic potential. The extra potential what we put is O potential, and this is on FTO glass, and this is on nickel foam. What we see, we have almost 240 millivolt of O potential. This is very low compared to other systems. And if you use nickel foam, we have only 120 millivolt of O potential. That means 120 volt of extra potential we require to reduce water. We also compared with other catalysts, the noble and non-noble, but what we see that platinum is the best catalyst for hydrogen evolution reaction. However, one should remember that this system doesn't work for oxygen evolution reaction. Still, we are the winners because we have oxygen evolution and also we have hydrogen evolution reaction with our catalyst. Similarly, the stability at 10 milliamp, that is minus 10 we tried, and we see that they are very, very stable. And we even get increased performance. So one of the interesting aspect of this work is the reversible switchability. That means you have this film, you apply oxygen evolution reaction, and you change your catalyst. That means your catalyst is no longer the same catalyst after you apply your potential. That means it's a pre-catalyst. And then if you apply the reverse, that is hydrogen evolution reaction potential, you are getting some light brown colored film. And then if you apply again positive potential or oxygen evolution potential, then you are again getting the same black colored film. So that means if you look at this way, so you form this catalyst, and then you can reversibly form this catalyst every time when you use it without losing any activity. Similarly, we can also do it for hydrogen evolution reaction. You take the catalyst, apply your potential, you can form this black colored film, which is equivalent to this one, and then you can reversibly produce it. So technically, it means that you can use your catalyst both at the anode and cathode. That's it. So this is clearly shown here. But important thing is that we don't lose any activity even if you switch the electrodes. This is the take-home message. So as I said, we are also interested to know what exactly happens to the catalyst. As I said, you take the helical borophosphate or any catalyst for that matter, but at the end of the day, what you are getting is something completely different. This is not going against the definition of a real ideal catalyst. When we looked at the scanning electron microscopy, this is the scanning electron microscopy picture, and you see that we have amorphous and crystalline core shell structure on the surface of the catalyst. This is the electron diffraction pattern. This is similar to X-ray diffraction. When you have such spot, that means that your material is crystalline. And when you have no diffraction pattern, there is no spot, that means your material is amorphous. Okay. And similarly, we checked after hydrogen evolution reaction, we have the same surface passivation, but in this case, we have a lot of reflection. That means our crystalline material is still crystalline. It didn't form amorphous shell as we could see here under oxygen evolution reaction. Okay, as I spoke about real in situ condition, that means operando condition, where we could see what happens to the catalyst in during the chemical reaction. Well, how could we check it? We could check from X-ray absorption spectroscopy. We have developed a method where we can uh, measure X-ray absorption spectroscopy in real condition. Now, we should know what is X-ray absorption spectroscopy if you are not familiar with the spectroscopic method. So X-ray absorption spectroscopy is a spectroscopy where you apply high energies and you excite the core electron. And when your atom or the your electron absorb enough of energy, it goes to the higher energy level. So what you see here, this is called X-ray absorption near edge spectroscopy, where from this spectra you can see what is the oxidation state of the material and what are the element. It is element specific. You could really tell what is the oxidation state. And then if you apply more energy, so you are kicking out this electron to the continuum. When this electron goes out of the system, it interacts with other atoms, and then you would get something like a interference. And this interference pattern is just shown here. This region is called X-SAFS region. This is the X-ray absorption fine structure. So, and from this spectra, we can understand the local atomic structure as well as the bond distance and coordination number. So it will give you some information which I'll show you in the next slide. So, okay, so this is how it looks like. This is the X-ray absorption near edge structure. What you can get here is the oxidation state. That's it. So this is what we measured for oxygen evolution reaction, and this is what we measure under hydrogen evolution reaction. And what we see here is that our material had oxidation state of +2 in the powder state. In the depositor state, we had slightly less oxidation state, which is still closer to 2. And then during hydrogen evolution reaction, our catalyst was completely reduced. Similarly, in the oxygen evolution reaction, our catalyst is completely oxidized. So this is the X-ray absorption fine structure. Don't be scared of this complicated diagram. What it says is only that this is exactly fits with our powder pattern with the crystal structure, and then under OER we are changing our structure to something called oxide structure, and in HER we are again getting a change structure. This is no surprise. I already told you that our structure, our catalyst doesn't remain the same. It changes during the course of our chemical reaction. What do we get? The final information what we get is when we use lithium borophosphate or lithium cobalt borophosphate or any pre-catalyst in our system, it changed the structure. In here, what we see is that 63% of the structure remained, almost 40% of the structure changed into something like cobalt oxide. Similarly, under hydrogen evolution condition, I'm talking about oxygen evolution reaction. For under hydrogen evolution condition, we got almost 50% of the initial product, but under also we get almost 40% of cobalt, only metallic cobalt, that is reduction of this material, and some amount of cobalt oxide. Okay, so finally to conclude something out of it, so we have a lithium borophosphate, which is the initial nice structure. If you apply hydrogen, let's say oxygen evolution potential, you change the structure into something like cobalt oxide, oxyhydroxide on top of lithium cobalt borophosphate. Similarly, if you put hydrogen evolution potential, you are forming metallic cobalt and oxide on top of cobalt, lithium cobalt borophosphate. This is somehow a general rule. If you take a catalyst in oxygen evolution reaction or hydrogen evolution reaction, your catalyst changes. That's the whole point. So we also did overall water splitting. That means, as I already told you, we need to show that it is good enough for an electrolyzer. So we use anode as well as cathode, the same material, which is lithium cobalt or sodium cobalt borophosphate. This is the cathode, this is the anode, and we could test for 3 months or more, 2.5 months, almost 3 months. We tested already this activity doesn't decrease. So this could be an ideal candidate to use commercially. And also, this is something called Faraday efficiency, which I told you in the beginning of the slide. That means how much charge we pass, how much current we get. Our efficiency is almost 100%. We can produce 100% of hydrogen and almost 98% of oxygen in the system. And the overall energetic efficiency what we reach is about 97%. So this is the video. If I can, I don't know whether I can play. Yeah, I can play the video. You could see how this whole electrochemical cell works. We are producing a tremendous amount of hydrogen here. You can see the gas bubbles. This is where we are producing oxygen. This is a two electrode cell in potassium hydroxide electrolyte. And if you practically collect your hydrogen and oxygen, you have to separate this in a two compartment cell, and you can individually collect your gases, hydrogen and oxygen simultaneously. Okay, to cut the story short, I would show you that I already showed you that we had made such an efficient system with a very diverse structural aspect. And this is one of the other report which we just published in Advanced Materials. This is similar to cobalt. We also made manganese, similar structure, and it also shows some completely different structure. And we could use this material for 5 months of stability. So this is really good. The system really works. So I think I do not have much time. How much time do I have? Can someone tell me?
10 to 15 minutes, sir.
Okay, thank you. So, okay, good. So I would like to show you a second class of compounds, which are also very emerging materials. So they are called intermetallic compounds. Now, we learned in our recent study that nitrites are very, very good materials for water splitting. Why? Because they're electronically very conducting. So what you could see here, these are the two published papers from us very recently. Electrically conductive core and catalytically active surface area is very important to run the catalysis. So we thought of, why don't we take a material which has a lot of conductivity, also very active on the surface, let's say active sites. So that moment we thought of intermetallic compounds. Intermetallic compounds, what are they? So you must have heard about alloys. Alloys is something like you mix a structure A, which is of the similar size, and with the structure B, and you form a composition which are called alloy. So you have like a solid solution. You mix nickel with cobalt with a similar structure, so you have nickel cobalt alloy. Or you can take a copper and nickel, you have copper nickel alloy. But intermetallics are very different from alloys. So what you do, you take a structure which is of a particular crystal structure, and then you take a metal C, which is of completely different structure. You mix these materials and you form a completely new structure with diverse properties. Okay, that is called intermetallics. So what are the properties of intermetallics? So intermetallics are very attractive because of its crystallography and electronic properties. They're very conductive. They have been already used for superconductivity, ferromagnetism, and so on. So they are well-studied materials for some different purposes. But for energy conversion and storage materials, they have not been used so far. So we looked into the literature and we saw that if you use the keyword metal and catalyst, you get lots of publications. If you use alloy and catalyst, you also gain a lot of, you see that a lot of publications being published every year. But you use intermetallic, there are no reports. You can see that there are only like 10, 20 reports for such large class of materials. This is our intention to explore completely unexplored class of materials. Okay, so what is known about them? So what you could see that they could be used in diverse energy applications. This has been proposed that they could be used for our purpose, for example, oxygen evolution reaction, for hydrogen evolution reaction here, hydrogen oxidation, and so on. So this is just to show you that they have a lot of potential to use in energy field. Okay, the first thing which came to our mind is we have to use a very highly conducting, because conductivity is very important aspect for water splitting. And we looked in the literature, and we saw that all these materials are very conducting. And from this we concluded that cobalt tin is very conducting, because there has been report in physics that they compared all these materials and showed that cobalt tin is the highly conducting materials, and it also have active center which is cobalt. So we thought, why don't we try this material for water splitting? How do we synthesize it? We synthesize in a very simple way. You take cobalt precursor and tin precursor, and if you use such a refluxing condition, we use this diffusion mechanism where the tin are slowly diffused under cobalt sites, and you form such a nice structure which is tetragonal. How does it look like? Again, very nice. Every cobalt atom is surrounded by 8 tin atoms, and it's more or less looks like a quadratic antiprism. And this antiprism is connected via different corners to form or edges to form three-dimensional network. This is the XRD pattern I want to show you. This is just to show that what we made is pure phase. This is the scanning electron microscopy. From transmission electron microscopy, we could see that there are very small nanoparticles. This is the high resolution. You see that they are almost 5 to 10 nanometer particles. This is the selected area diffraction pattern. This rings show that the material is very nanocrystalline, and this is the numbers show that these are responsible for certain number of planes, such as this one. Yeah, so this is easy to understand that we made a new phase pure material. And this is X-ray photoelectron spectroscopy. If you are not familiar with photoelectron spectroscopy, this is just to know the oxidation state of the material on the surface. That's it. So what you see here, that our material has a lot of cobalt zero. There's metallic cobalt, which we expect for our cobalt into material, and also we have tin zero material. That means our cobalt tin is intermetallic with oxidation state close to zero and slight oxidation. This is due to the passivation. Okay, this is the activity of our material. What you see here, that cobalt tin is much better for oxygen evolution reaction, also for hydrogen evolution reaction. But it again, platinum is still the best for hydrogen evolution reaction. However, if you look at the O potential, we are gaining a much lower O potential, which is almost 238 millivolt for oxygen evolution reaction, and very low, which is almost 95 millivolt for hydrogen evolution reaction. At different potentials, we apply at 10 milliamp. We show that most of the catalysts are not stable, but if you look at this cobalt tin 2, which is very stable, also over here, and we are getting only improved let's say conductivity and activity. This is just to show that what happens to the material. As I told you, no catalyst remains stable under these conditions. We saw completely amorphous material after our oxygen evolution reaction. However, in the hydrogen evolution condition, we still see these rings. That means our material did not change much. Same we tried with oxidase analysis, which showed that most of the material got oxidized. This is because we are using a highly alkaline condition of potassium hydroxide. So it's expected that most of the catalyst would oxidize. This is just to show you that how the oxygen 1s spectra looks like in XPS. It shows that we have formed oxide phase in OER, but HER nothing changed much. We also constructed an electrolyzer to produce hydrogen and oxygen. This is some of the activities. I don't have so much time, so I just show you that we get almost 1.55 volt of cell voltage, which is extremely good for a water splitting system. And this is how we calculate the Faraday efficiency. You could see that if you run an electrolyzer, this is the anode and cathode. What you are getting here is hydrogen and oxygen on the top. We could measure it, and you can also plot it. You can see how much ratios you got, how much efficiency you got. To show you a small summary, we have made tin and cobalt, and it diffuse structure, it forms cobalt tin 2, and in the case of OER, all our tin get dissolved and we have only cobalt oxide left. And in the hydrogen elution reaction, we are only diffusing the surface cobalt, or you can only dissolving the surface tin material, but we are all the cobalt and tin inside the material is intact. Okay, I have no time for this. I just want to show you that we also made some other intermetallics, which is manganese galide, very nice structure, uh, big particles. We did all other techniques. We did also electrochemistry. And what I want to show you that they are also not stable under this condition, and they actually form different structures. So we start with manganese galide, and at the end we form manganese oxide, manganese oxyhydroxide, and bernicite type structure. So our material is not stable under this condition. Um, I will just show you some of our recent work, what we did. We also use other intermetallics such as iron tin 2, and we show that we can produce a lot of oxygen evolution reaction. And this is the first time we also used this material for organic oxidation. So we took HMF, 5-hydroxymethyl furfural. It's a very important substrate in polymer chemistry. And then we oxidize this thing with oxygen, molecular oxygen, under this electrochemical condition to form FDCA, 2,5-fluorodicarboxylic acid, which is a very important or valuable chemical in polymer industry, as I said. Okay, so we also look forward for future directions. So this is one of our recent report where we used a cobalt selenide structure and we could make diverse structure out of it. This is the pre-catalyst. Nothing remains stable. This is the take-home message. Every catalyst we use transforms into something else, either useful one or completely useless one. So at least in this case, we got one useful material and it was very active. And also we look forward for such future direction where we could use the molecular precursor and we can form some nice heterostructure. I have no time to explain this, but you can go through these papers, which is published very recently. And also, not only water splitting, we also are looking forward to do some more chemistry with it, such as CO2 reduction, and also reduction of some very important bonds such as phosphorus oxygen, silicon oxygen, and sulfur oxides through electrochemistry, and to break them and to make some valuable chemicals. Finally, I would like to thank my group and my collaborators and my former and present members and the funding agencies, and a very small information for the students, if some students are listening to this talk, and also the faculties. We have several opportunities for research and collaborations in Berlin. So there is a graduate school in Berlin, which is called Big NSC. So if you are MSc students and if you like to come to Germany to pursue your PhD, you could go through this site. And we have diverse areas where one could apply for, and then you could really come here and do your PhD, if you're interested, of course. And then we also have something like BUSCAT, which is the collaboration between the university and the BASF, which is the largest chemical company in Germany. If you're interested to do some project work, you can apply there directly on this site. Maybe you can come here for 6 months to do your master's project or bachelor's project, something like that. And for the faculties, we have something like UNICISCAT, where we work on concepts in catalysis, which is called Unifying System in Catalysis. We have diverse areas here. You can also go on this site and you can check. If you're interested, you can write to the respective people and you could have a fruitful collaboration in future. With this, I end my talk, and I really thank you for your kind invitation, and I'm open for any questions.
Thank you, sir.
Very much.
Yeah. Yeah. Now the floor is left for open discussion. Participants, you can interact with Dr. Prasanth. If you have any queries, feel free to ask him. Yeah.
Hi Prasanth, this is Manoj speaking from Calicut. May
Yeah,
you
hi,
have your
Manoj.
class? I'm proud to hear your lecture after a long time. Though you're my
Mm,
classmate, I could not speak with you. My question is,
mm.
how easy is it to synthesize these intermetallic molecular compounds? But you have shown just a one reduction reaction, but is it always, do you get a very pure form of the intermetallic compounds, or even your this nano catalyst? Is it a mixture of things are possible, or you is it easy to purify and get your the catalyst what you require, the crystal structure and all other things? That's my one question.
Okay. Thank. Okay. Thank you, Manoj. It's a very nice question. In fact, yes. So normally the intermetallics are formed by high temperature techniques. Uh, okay. Okay. I have some
Ah,
disturbance here. Okay.
Manoj,
Yeah.
please mute your mic. Yeah, we are having some sound disturbances.
Okay. Manoj, can you hear me?
Yes,
Okay.
I can hear you. Yes.
Okay. Thank you. Thanks, Manoj. So, as I said, it's a very good question. Normally, intermetallics are formed by very high temperature techniques because you need some kind of arc melting, or you take your elements at very high temperature, like mostly over 1,000, and fuse them. Normally, if you do it via high temperature, you're always forming some kind of impurities, but it is still possible to form very pure intermetallics, but it takes a lot of time. But if you look at in this way, if you make any material in very high temperature, you are consuming, or let's say you are using a lot of energy. So this makes us very problematic because we want to use very cheap materials, and also bigger the particle, lower the surface area, so it's useless for us. That's why what I showed you for cobalt in case, we started with the solution technique. So this works very fine. So if you take a stoichiometric amount of cobalt salt and tin salt, so you really end up forming very pure cobalt tin compounds. But this is not true for all materials. Of course, if you use, I mean, you need the right conditions. If you use little bit of higher concentration of tin or cobalt, you end up with metallic cobalt or metallic tin, which we don't want to have in our system. So we want to have completely pure system. So therefore, this is a very tricky synthesis. So we should really know. I mean, it's not that you cannot predict it. Like you cannot go and say, okay, I'm going to use 1:2 and I form 1:2. No, not possible. So we have to really play a little bit. And if we can, when we find the right condition, we can really use it, and we can make in a very pure form. And also, we have discovered that if you start with a molecular precursor, if you take a molecular precursor, if you take a material, let's say a complex with certain ligands, and if you treat it at high temperature in a hot injection technique, usually form very pure compounds, because all the other the molecular component will be in dissolved form. So you are forming less carbon contaminant, and your purity will be much higher. So those materials are very, or let's say they are very they're in nano form. So you could really use this material as a high surface area electrodes. So this is very good for our, let's say, our work.
Yeah, thank you, Prashant. Thank you very much.
So,
Yes.
in the synthesis of intermetallic synthesis of COSN2 nanocrystals, you are using
Yeah.
PEG.
Yeah.
So what is the purpose of using PEG in that synthesis?
This is simply a structure directing agent. So this actually holds the nano form. And it helps in nucleation. It brings the whole nucleation together, so that we can only form nanoparticles, because we don't want to have bigger particles. So we want to be, let's say, sequestering agent in nano form. Like you really somehow hold this structure in a very nano form. This is you can also use some other let's say polymers or other agents to direct your structure. So this is also possible. I mean, we just took it from since we are using those for a very long time, we just used it as a, yeah.
Okay, thank you, sir. Thank you, sir.
Any other questions?
are these substances economically viable, or can be economically, what is the outcome? That is it a costly affair or a?
See, in the water splitting system, the main important part is the efficiency. Okay, so
Yeah.
if you look at the electrolyzers, if you look at the electrolyzer, they are using iridium, platinum, and so on for at least acidic electrolyzers. It's very, very expensive. You know the amount, the
Yeah.
price for platinum and iridium. Yeah,
Yes.
and the aim is to come to cheaper materials, but if you come to cheaper materials, this proton exchange electrolyzer doesn't work, because this is as simple as that. They dissolve because it's acidic. It is in acidic
Yeah.
condition.
Yes.
Then we have to rely on alkaline electrolysis, because there our transition metals are more stable. Now these materials what we produce are comparatively very, very cheap. So now this we are in a process to show that how we can reduce the over potential, which I told you that the over potential should be close to zero. Yeah, the first step is to design a catalyst which works, and we want to know the fundamental understanding. Once we design those catalysts, we can tune them according to the way we want. Maybe we can tune them into a very porous structure. We make very porous structure with very high surface area, then we have benefits. Secondly, we can tune their electronic conductivity. So that the moment our hole and electrons are separated, we can immediately take the electron. Yeah, this is all. There are a lot of possibilities, and we can also tune the electronic structure, and we can tune the specific structure, and so on. There are a lot of opportunities are there. But the first thing is we have to find a material which works not for one day, not for 1 week, for years, 10 to 20 years. This is the task for us, and to make it in a very low, let's say, in low, high efficiency, low cost. Yeah, that's the main aim. And if you look at the electrolyzers, they do not operate at room temperature. They're all operating at high temperature. So we want a catalyst which stays just like that at 80 degrees or 70 degrees without undergoing any transformation. And if which it undergoes a transformation, is dead after 1 week, then it's useless anyway. So if you want to do it commercially, we have to understand the facts and understand the chemistry, and you have to come out with the best catalyst. That's the aim presently for this field.
Thank you, sir.
Yeah, well, that's a very good question, of course. Yeah.
Thank you, sir.
Any questions from student side? Okay, sir, I hope there are no more questions. So I request Professor Christina Maria Matthew for the vote of thanks.
Um, Good evening, all. Respected Head of the Department, Dr. Suma Bino Thomas, our Speaker of the Day, Dr. Prasanth Menezes, all the participants, and my dear colleagues. Today, we had an interesting session by Dr. Prasanth Menezes on emerging materials for energy-driven water splitting. We know that 71% of the earth is covered by water, and one seldom realizes the difficulty in splitting water to hydrogen and oxygen. Sir, the session was really informative and gave an insight into the photocatalytic and electrocatalytic water splitting. And on behalf of the chemistry department and all the participants, I extend my sincere gratitude to our speaker, Dr. Prasanth Menezes, for sharing your knowledge with us. Thank you, sir.
Thank you.
I would like to place my deep sense of gratitude to our principal, Dr. Viju Thomas, for his support to all our endeavors. Next, I wish to express my sincere gratitude to our head of the department, Dr. Sima Vinod Thomas, who is the guiding force behind this program. I also extend my thanks to Dr. Jinta Thomas, the coordinator of the program, for organizing such a wonderful webinar series. I also wish to express my gratitude to organizing committee, all the members of organizing committee for their support and hard work. Last but not the least, I express my heartfelt gratitude to all the participants who made this webinar a grand success. Thank you. Thank you.
Thank you. So we have a question for Gopi Setti Harshini.
Yes. Yes.
Yeah, she's asking about whether we need to have a German proficiency to do PhD in Germany.
Well, in principle, no. If you are coming for PhD, usually you don't require German proficiency. You can come here and then probably, depending on the universities, you have to take classes, like basic classes. But it would be an advantage if you take classes in India, at least the A1 level, and then apply. Then they could see that you already have, the German proficiency, and then it's easier to get the position. Most importantly, because most of the technical staff in the university, they don't speak English. So if you already speak little bit of German, they'll be very friendly with you, and your things will be much, or your, whatever you need for your experiment, or this, maybe the glassware, the chemicals, or whatever, will be much faster. And they really like it that you learn little bit and you try to converse with them, and finally they will be very helpful. And this is also a significant criteria when you hire somebody. You see that somebody has like A1 level of German, and you say, okay, he's willing to learn. This is also taken into in a positive way. But I think if you want to come as a master student, then probably I think you should have some, let's say, A1 level. They want to have a certificate from you. But PhD, technically, no, you don't have to have.
Okay, thank you, sir.
No problem.
Okay. So I request the participants to kindly fill the feedback form. Thank you very much, Dr. Prashant. And we will be
Yeah.
having our last session of, yes, thank you, sir,
Thank you.
of series on 19th December, which will be handled by Dr. Gopakumar Gopinathan on the topic application of nanoparticles in cancer therapy and diagnosis. So we solicit your esteemed presence for the same. Thank you all once again. Have a nice time ahead. Thank you.
Thank you.